Hello.
Hello.
Hi.
Hey, sorry I'm a little bit late.
No worries.
How you doing?
Good. How are you?
Good. Where are you calling from?
Seattle.
Seattle. Okay.
Where are you?
I'm from San Francisco right now.
All right.
Yeah. Um, cool. So, do you have anything in particular you want to practice?
Well, I'm preparing for Google and Facebook interviews. So if you know what kind of phone interviews they have, that would be great. Other than that, I didn't have anything in particular in mind.
Okay. So I work at LinkedIn. I can give you interview questions of similar difficulty. I know that uh, Geeks for Geeks has really good coding questions, and then they list off questions by company. So I can give you some Google or Facebook questions.
Okay. Yeah, that sounds good.
Cool. All right. What would you say what kind of difficulty level are you going for here? I don't want to give you anything too easy. It doesn't make it very.
Probably medium is good. I don't, but yeah, medium is fine. Probably. Yeah.
All right. Let's do this one. This one's hard. Also hard. Pull right through. Um, all right. Here's a medium.
All right.
So, all right. I don't know Go syntax, so I'm just gonna get in the comments.
Okay.
So I'm gonna give you an array. It's gonna look like something like this. Okay. It's gonna look something like that, and then I'm also gonna give you a number.
Okay.
I'd like for you to write a function that determines two numbers in the array that when the first number is subtracted by the second number equals to the number I provided.
So subtract the first one from the second one, and return what the index is, or
The numbers themselves is fine.
okay. All right. Cool. So um, well, I could just walk the array and then compare each number to well, not compare, but try to match the numbers one to another. Um, and then if I find a pair, I just print them or return them. That would be a quadratic because I'll have to compare each number to the rest of the numbers. Basically like a double for loop. To do it faster, I could just walk the array and then kind of keep track of what I encountered so far, and then like a hash map, and then consult that hash map for each next number, and see if there's a match. So I'm probably going to go with that. So that's going to be a linear time. Does that make sense?
Mm-hmm.
All right. Yeah, go ahead.
Yeah. So Why don't you do that? I can ask a follow-up question after.
Okay, cool. So I'm gonna in Go. You said that you didn't know the going syntax, but it's somewhat C-like, so it should be pretty straightforward. All right, so I'm going to create a hash map of an integer to an integer. What I'm going to keep, probably going to in the map, the key is going to be the value of the item in the array, and then the value is going to be the index at which the number is at. So let me try this. And this is a main function. Let me write the actual function. Fine. And have first and return return couple of events. And I guess an error if we didn't find anything. Wow. It just be all right. All right. So app with the hash table, and then length of n, and then let me see, how should I do this? Should look if and the target number. That's right. Target integer. And you said subtract first one from the second one, right? Or
yeah, I mean, the order that you return them should be such that a minus b equals the number I provided.
A minus b. Okay, got it. All right. Say difference is going to be minus target. Also, let's see. Minus b equals target. Then, if we're looking for, say, b, then it should be plus target. No, minus target. Okay. So if if it exists in the map, if then we've found the numbers, and then we'll just return int of and well, I guess the diff. Otherwise, we are going to insert. What we're going to insert there? I think the number itself should be inserted in there. And well, the index would do. So let me see. So come here, and the difference is going to be 78 minus 5, 73. Well, it doesn't exist, and then we'll insert 5. Try this here. Maybe 5 is there. We'll come next, 20, and then 20 minus 78. Where is it? 20 minus 78 minus 58. So it doesn't exist, so we'll just insert 20. Then 3 doesn't match again. 2 and 50. And then we'll come to 80. So we'll do 80 minus 78 is 2. So we'll find 2. and then we insert 80, and then we insert 2. So that should work. All right, let me test that. Integers, and I'm just going to copy what you have here. And then 8, and then I'm going to just print the call to this function. Number, and okay, let's run it. T must be there. All right, so that seems to work. Is that? Yeah.
Yeah. Okay, so this is probably too easy for you.
It's yeah, it wasn't too hard. I guess it just clicked. We can do another one if you want to. Well,
yeah, let's do another one.
All right.
That's a confidence booster. That's a warm-up question right there.
All right. Yeah.
All right. This one's a medium, a real medium.
Okay.
So this one's called count all possible paths. The idea is maybe you're really math oriented. You can just figure out the formula for this, but most programmers are not.
Okay.
And so they will basically run a simulation to figure out the answer here. So the idea is provided a grid, sort of like.
Oh yeah, I love grids. For some reason, those things just click with me. But yeah, let's continue. Sorry.
All right. Well, maybe this will be easy too. So provided a grid where the substance of the grid is really the edges, right? So it's you can think of it as a bunch of equidistant points and then edges between those points.
Okay.
And it's a M by N grid.
Okay.
In terms of lengths of number of edges on each side. So it's a rectangular grid. And the idea is that you start on the top left, and you want to finish at the bottom right. And the idea is to count the number of ways that you can define a path from the top left to the bottom right, given the rule that you can only go right or down at any given. Let's see. Peaceful person. Should know this.
Okay, and then you mentioned that there's something in the the cells themselves. Is there like numbers? Do they matter, or it doesn't really matter? It's just a grid.
They don't matter. You're just trying to count the number of different ways.
Okay, cool. So I'm gonna usually what I do with the grids, I like I said, like start at the left, top left, and then I recursively call the directions that I'm allowed to go to. For example, right and down, and then I calculate the number. I need to calculate the number of ways I can get to the final point, right? So okay, let me think about this. So if I start here, and then I have a little notebook here. I'm trying to visualize the grid. So if I go right, that's one path, and from there, and then I see. So okay, All right, so I'm gonna go to each neighbor, well, write them down, and then recursively go everywhere else from there. And then what I'm gonna return is um, the what am I gonna return? I'm gonna return the number of uh, ways I can get there. And so how would they do that? So say go right, go right, go right. Can't go there. I'm gonna go down. So all right, if I go right all the time, then I reach the point, and then if I come with you, then I return, and I say, well, I reached it, so that's one. Then is there any other way? No, not from there. And all the way back, so it's one. That's two. Okay, so let me try that. So I'm gonna just recursively call it and return each recursive call is gonna return a Boolean, let's say true for if it actually reached the destination through recursion down the path, or false if it didn't. And then I have to accumulate the numbers somewhere. So maybe it's not a Boolean, maybe it's an integer that I need to. Let me see. Return them. Can't go anywhere here. All right, so it's true. Okay, plus one, and then okay. Yeah, it will have to be an integer. All right, so let me try to code it up, and then I'll see how it goes. So we'll have. Do you mind if I just delete the other function, or does it matter if it stays there? Well, I'll let it stay there. Okay. So I'll have a function walk cell. Then I'll have a grid, maybe just a matrix, and then I will get row, and I will get column index, and I'll just pass the size of the matrix here, and then let's say it returns an integer. All right, so after that, so we'll come here, and we only can go right. Well, I guess if we only are allowed to go right and down, we cannot intersect with we cannot intersect our own path, I guess, while we're trying to reach there. So that should be fine. So then go right. If C smaller than C minus 1, if it's smaller than C minus 1, we can go right. So we'll just go and say right. And then we'll say, okay, go right and figure out the number of ways to get there. We'll do grids, what? Same row, column plus one, CR, and yeah, and then the same for the left. Oh, down, not left. Go down and down. And that means that the row index should be list one before last. So we'll walk R plus 1, same column, and then return plus I'm down, but we need the base case. So base case is going to be if R equals, well, I guess R, and no, R minus 1, and C equals, C minus 1. That's the last. Then we just simply return just 1. I guess that should work. So come here, we get our 1. Come back, that's 1. It's 2. Okay, and here, same grid. Yeah, it's gonna be make integer size. I don't know. Let's try 4, and then for each row in there. This 4 rows, 4 columns. Row, within row. We will populate grid R. Let's make and of size C. And then we will print. What do we print? Oh yeah, just gonna Excel grid 0, 0, and then R and C. Let's run that. 20. Let me see. So 1 and 2. Yeah, that definitely is not correct. So 4x4 grid, there will be exactly 2 paths that we can reach the top left to the top to the bottom right. So let me see where I got it wrong.
Just 2.
What's that?
Just 2 paths. I mean, if it's 4x4, right?
Oh, I'm sorry. This is 2x2. Yes, I just drew 2x2. 4x4 would be a bigger matrix. Yeah, that's right. Let me try that. Well, actually, since I did 2x2, let me try 2x2. 2x2 does give us 2. All right, so let me try 4x4. Well, what about 2x3? So 2 rows and 3 columns is going to be 1, 2, 3. I think 3. Yeah, it seems to be working. It did give me the right answer for two small samples there.
Let's try running it with try running it with 3 and 4.
3 rows and 4 columns, that is, right?
Yes.
Yeah. So it says 10, the answer for 3 rows and 4 columns.
I think that's correct.
All right.
Nice.
Yeah, like I said, I for some reason I can visualize the grids in my head very easy now. Trees or something like that is a little harder to visualize. I don't know. Maybe it's different for. Sure. If we have time, yeah, of course we can do a little tree thing. Why not?
All right. Um, okay. This one is called Falling Leaves. We give you a tree, and let's say you draw that. And a tree like this, and we'd like you to output a list of lists where the first index in the sort of outer list is a list of leaves that would fall off the tree if this was a normal tree and the leaves fell. And the next list is the second set of leaves that would fall off the tree, hypothetically. And the last list should be the leaves.
Oh, okay. So basically, we need to get to the leaves and then kind of remove them. Well, print them or add them to the list, and then do the rest of the tree as if we were, say, to remove those leaves, right?
That's right. As if we don't actually remove leaves.
Right. Okay. So we need to do the leaves first. All right. Well, so we can easily get to the leaves, right, recursively, and just collect them all once we get to a node that doesn't have any left or right children. We add it to some list, but at that point we'll traverse the whole tree already, and then after that we need to get to the rest. So you said that we cannot kind of modify the tree, the input tree whatsoever, because if we could just kind of cut off the leaves that we found, that would be easy. Well,
what we could do is
we could pretend that we're cutting them off, because really there's nothing. All right, yeah, that's right. So it's pretty much going to be a well, no, that's not going to be like an order traversal, because I have to get D and E, so that's easy. But then the next one I need to get is the C, so I can't go back to B and say, oh, no, oh well. Let me see if I can do it. So when we return from D and E, we know how do we know? Well, okay, so if I were to, to say, okay, so this is going to be linear time no matter what. I mean, at least linear, because we have to visit all the nodes at least once. And let's say I'm gonna, traverse the tree more than once. So say I first traverse the whole tree and find the first set of leaves, right? And I just stick the values into a hash map. And then I traverse it again, and then at this point, what I do is I traverse it and see if the children of a given node are in that hash map that we just populated. And then I create another hash map and then insert that node in. Well, that's Yeah, it's just going to be 2 hash maps. And then that will give me the second level, that is B. That is B. So D and E are there. So I'm going to get B. And then I go back to A. C is not going to be already. And then after that, I add this to the list and I get another hash map. All right, that will work. I don't like the additional. So I'll need 2 hash maps for this, and then I'll have to traverse the tree multiple times. Actually, how many times will I have to traverse it? Well, it depends on how many leaves we have. So, I mean, it's still going to be linear, but it's definitely not a single traversal. So what do you think about this? I mean, this is not probably the optimal way to do this.
Yeah, so I think the traversal approach is definitely not optimal from a space perspective.
Okay, so you're saying we could probably do it in a single traversal?
Yeah.
Okay.
You can do it in a single traversal with only your result list.
With only what?
List. Only with, you have a mutating result list, and then you do
right. Yeah, gotcha. All right, let me think. So okay, so I get to the leaf, and well, I do have the level, but the level doesn't. If I pass the level, and it doesn't really give me much. Oh, okay. So I could get to the first one. Say I do always go to the left node first all the time. So I would start from the root, which is A, and then go to B, and then go to D. Okay, D is the leaf. So I return back, and I could return like an integer. So say every leaf is going to be 0, level 0. So I will add, so because it's a list of lists, so all the leaves, if I consider them level 0, then I will populate the first list and the list of lists. And then when I return back to B, I will say, well, that was a leaf, and I will return 1. And so I populate the second thing there. After I return from right, and then from B I could return 2, and so the A will know to be added to 2. Yeah, that could work. So if I kind of work bottom up fashion, where I get to the leaves first and then start populating the list of lists from there, and then I just indicate how many levels the previous call is away from the leaf. So that is, when I return back from D to B, I will say, oh, you're level 1, which means that you're just above a leaf node. So that could probably work. Do you want me to try and code that?
Yeah, one question now. What happens when you get back to A? So you basically have to deal with.
So when I get back to A, B will return 2. Oh, I see. And C will return 1. How should I handle that? I should probably take the larger number, because, like, if, for example, D wasn't, we should probably look at what the left recursion returned and the right recursion returned, and just pick the maximum number out of those two and kind of stick it in there. So that way A is going to be level 2, B will return 2, and then C will return 1. So A will say, well, B has a higher depth, so we'll take that.
Cool, that makes sense.
All right, so I'll do node struct, and it's going to be well, some value. Oops. And then left and right. It's going to be, and so I'll have a function walk node. I'll have a pointer to the nodes, and what else do I want? Well, nothing. And I'm going to turn an integer here, and I will say well, let's do this. If it's a null, I don't want to pass a null in, so I'm not going to check for here. So I'll just say left step is going to be going to be 0, and if n dot equals null, we will walk it, and we'll say there's going to be walk node and left. Okay, and then do the same for the right side. And the right depth and right, and the right depth is going to be fine. And then oh, I need the array. That's right. So I should I pass it? Well, is it okay if I make the list of lists a global variable kind of?
Yeah, I guess so. I mean, you could imagine it as an object-oriented thing, but
well, problem with Golang, it doesn't have array lists, so I'll have to like re-add them all the time, and that's well, I guess it's fine. All right, then. So I can't just like array push or something. I guess I could create a structure to do that, but I'll just go with this. So I constantly like redefine it and have to return a new pointer. That's the pain. But yeah, that's the list of lists, and then I will say results, because this is where, so then I'll have to pass it in this. And then what do I want to do? Oh, I want to find a max. Well, if is larger than the right one, then we'll stick it into, where is it? Into the level to, I'll say if length of this is less or equal, then we'll say rs. And this is what I'm talking about. You have to like constantly resizing the arrays. So, well, yeah, integer, and then and then it's going to be m val. So we grow it. If we don't have the level yet, we add the level, and then we just grow that thing. And the same here. And I could probably get by with, sorry, I'll do depth equals math dot max of cleaner. And we do this, and then we turn the new thing. So let's see. Here, make and yeah, I'll have to test somehow, but let me see. So that well, okay. So if let me see here. So how do we get to the leaf node? So we start with the root and go and go and go and go. And we'll find the leaf node. How do we find it? So if and left equals nil and that right equals this is going to be our base case, then we'll just simply say we need to add this. We need to execute this guy. If length of the rest is 0, meaning we didn't add nothing yet, then we'll just say this equals rest append this new array, and then we do this. Yes, so let me do this. So once we get to the leaf, we just simply insert it into level 0. And then we return res. Oh, we need to return 2. So we will return 1 and res. And then if not, we go and traverse the left and the right if we can. And what do we do? We insert it. All right, so let me try. Where is D? So D will get inserted first, and then we'll return 1. So we come back for B. We'll go to E. E gets inserted, and then here we'll receive both L depth and R depth 1s. So it's going to be 1. It's smaller than 1. No, it's going to be 1. Oh, so less or equal. Then we'll append a new one, and then we'll say res of 1 append. Yes, this will work. And here we'll return, what will return? The rest, and then also the max depth plus 1. So that will make it such that A will receive 2. All right, so this should work. This is our base case for the recursion to terminate at the leaf nodes, and we'll basically just keep populating the first list and the lists. And then we go.
Why are you returning the result?
So what happens in Golang? So you see how like the array. Well, so array type is a pointer, and you can modify the array elements. But once you call this append, which is like growing it, so like say you have 3 elements and you're adding the 4th, and what that does, it basically allocates new memory, copies the whole thing over, and then you've got a new pointer. So that's what I was mentioning, saying that it's a pain. I mean, you wouldn't do that in, for normal code, like passing arrays around and kind of, appending, recreating all. Yeah. I would usually use like a array list where you can just like create one pointer and then just like push into it, and then you just have to pass it around. You don't have to return it. That's why I suggest, like, if I made a global variable, then I wouldn't have to return it. But Yeah, it's
Okay.
kind of cumbersome.
So I'm looking at line 51 and line 55. It looks like you're binding to res twice there. Is that not a big deal because of scope?
Wait, say that again. So what happens twice?
So on 51, you're binding the second result walk node to res, and then on 55, you're also binding it to res. Now I don't know
Right.
Go enough to know if
Yeah. So that's the same thing. So both of the recursive calls might have changed the res, right? Because you recurse down some node, and it will change. So you have to get back the new pointer, so you can pass it up, right? And yeah, it's
okay.
That's why you have to like pass it around, because like once you call append, it will basically take this res that exists and create a new pointer, copy the existing values, add new empty array or whatever else you do, and then return the new pointer. So you gotta save it and kind of pass it up. So, but like if I had a
I understand that, but it looks like you're calling walk node and you're passing res down to it on line 51, and then it returns a res pointer that may be the same pointer, but it might be a different pointer, right?
That is correct. Yep.
Right, and then on line 55, you
pass it again. Yeah.
Yeah.
So it's like I'm just passing a pointer around, but it's like a variable that I have to keep track of and return everywhere.
Yes.
It's it's a pain. But
yeah, that makes sense. I'm thinking of this from an immutable perspective. Changes it. Okay, cool.
Yeah.
All
right, cool. Well, yeah, that was that was helpful. Yeah.
All right. Next time you should ask for hard questions.
Okay. Yeah. Maybe you're right. I'll try to do that next time.
You're ready for it.
Well.
Yeah. All right. Well, best of luck for your job search. I think you'll do well.